Okay, so we're going to look at how does one do a double integral if we're working in a polar space. So the first thing we have to understand is that we have to redefine the rectangle. So we're going to get a polar rectangle. Okay, so the idea here is, all right, so here I'm in the plane and I have some ray sticking up this way and it's pointing at some theta value, theta 1, all right? And then I've got another ray sticking up this way that's pointing at another angle measure, theta 2, right? So this is a rotational measure counterclockwise. And then what I'm going to do is I'm going to come up with two circles, right? So there's one on the inside and one on the outside, right? So this circle here is x squared plus y squared is equal to r1 squared. This circle on the outside is x squared plus y squared is equal to r2 squared. And this region here is going to be my polar rectangle. So the rectangle is the set of all polar coordinates r theta such that r is bound between r1 and r2, and theta is going to be bound between theta 1 and theta 2. So this is how we're going to define a rectangle in polar coordinates. So we're going to try to apply like the Riemann thinking to this a little bit and see how this plays out. Okay, so in our Riemannish thinking here, we're going to start out and we're just going to work in the first quadrant here. And I have a ray coming out this way and another ray coming out this way. And I have an arc connecting them, part of a circle there. And I have an arc connecting them here. And this we're going to call alpha. And we're going to call this one beta. And we're going to say that this little radius from here to here, we're going to say that that radius is length A. And we're going to say that this longer radius from here to here, that radius is length B. Okay, so what we're going to do is we're going to break this into like pieces, like we've done before. Okay, so we're going to kind of build radii this way. And we're going to build rays coming the other way. Okay, so let's look at what we've done here. This is R1, right? R2. R2. And then what we're going to do is travel a little bit here, and we'll call this one R, like I minus 1. We call this one Ri, right? This one is ultimately going to be Rn. So we broke that into n pieces, right? And then theta-wise, right, so this is theta 1, theta 2. We travel to theta j minus 1, theta j. This would be like theta m minus 1, theta m. So we broke that into m pieces. Okay, this time, though, instead of picking an arbitrary point inside each square, we're going to pick a very specific point. So this is the point that we're going to pick, right? And that point is going to be our I star and our J star. Okay, so it's the one between I minus 1 and I, and J minus 1 and J. But this is not going to be as arbitrary. It could be arbitrary, but for the ease of calculation, we're going to pick a very specific point within that rectangle. Okay, so the very specific point I'm going to pick, we're going to make our I star to be the point that's halfway between our I minus 1 and our I, so it's the midpoint that way. And it's going to be the ray halfway between, so theta J star is going to be halfway between theta J minus 1 and theta J. So it's kind of the midpoint of those. So the challenge here, though, is you're going to notice, if you go back to looking at that picture of the rectangles, is that they're not all the same size. Okay, the subrectangles are bigger as they go out, but the ones that are the same distance from the origin all have the same area. So we're going to let A sub I be the area of a rectangle, area of the rectangle that Ri star theta J star lives in. Okay, because only the distance from the origin matters here. So we can index that just with the radius. We don't need the J index in this. Okay, so this is going to be what we're going to use to get the delta A in our Riemann formulation. Okay, so each of these rectangles is actually geometrically a sector. So we need to deal with their area size and how that fluctuates with respect to I. Okay, so let's draw like the little sub-rectangle here, right? And see if we can kind of make sense of this. All right, so we're kind of back to this drawing, just like a rectangle. An arc there, an arc there, right? This one's at theta 1, that one's at theta 2. This length is R1. This whole length here is R2. And we're going to try to find the area of this thing, right? So let's do some calculating. Area here is going to be, well, whatever is the change in theta, right? So that's like theta 2 minus theta 1. So we're going to say that that's the change in theta out of 2 pi, because that's like what portion of the whole circle I have, right? And this is the area of the big circle minus the area of the small circle. Okay, so let's think about what that means, right? So area is theta, or delta theta 2 pi, right? And this is going to be pi times r2 squared minus pi times r1 squared, the big circle minus the small circle, right? Well, the pi's here cancel. That's nice, right? So this works out to be 1/2 delta theta r2 squared minus r1 squared. Okay, so let's think this all through, right? This is a difference of perfect squares. So if I write that out, I get 1/2, right? All right, so let's pause that for a second and get some more space to work with here. Okay, so if I'm working with the AI specifically, right, the R2 in that case is Ri squared, because that's the outer circle, right? Minus the R1 is R minus I minus 1 squared. That's the inner circle. Okay, d delta theta, right? So let's play this out a little bit here. We're going to get 1/2. Okay, so this is a difference of perfect squares, so that's R I plus Ri minus 1 Ri minus Ri minus 1 delta theta, right? So what do I have here? This is what we defined very carefully as Ri star. Aha, that's helpful. This is the change in R, so that's delta R times delta theta. So we can start kind of branding a bit of an integral here. All right, so the double integral over this rectangle of f of x, y, delta a, right, is the double integral over r, f of r cosine theta, r sine theta times delta a. And if we break that down into kind of Riemannish thinking, this is going to be I equals 1 to infinity, j equals 1 to infinity, f of r star I cosine theta j star r I star sine theta j star, right, times r star I delta r delta theta. Okay, so breaking that into a calculatable double integral, we're going to put the d thetas on the outside, the dr's on the inside. So this is going from alpha to beta. That's going from a to b. This is f of r cosine theta times r sine theta. R, that's this thing, r dr d theta. Aha. So the interesting thing about this formula is it gives us an extra r that comes out of the floating size of the sectors. Because the rectangles change size as they're getting larger, they're dependent upon the radius, and because we carefully crafted this, out pops that r in this calculatable formula. So let's actually use this to find an integral, an area, using this. So let's see what happens. Okay, so let's say we want to find over some region r 3x plus 4y squared dA. Then we're going to let r be x, y, such that y is greater than or equal to 0, and 1 is less than or equal to x squared plus y squared is less than or equal to 4. So if we think about what this looks like, where y is greater than 0, so I'm in the first and second quadrants, right? I'm here with a radius of 1, right? I'm here now with a radius of 2, right? So that kind of gives me what's going on here. All right, so this is the domain that I'm integrating this guy over. All right, so let's see how this sets up as a polar integral. Okay, so I'm taking the double integral over r of 3x plus 4y squared dA should be the integral from 0 to pi, because I'm only going halfway around the circle, times the integral from 1 to 2. That's the change in theta. That's the change in the radius, right? So this is going to give me 3r cosine theta plus 4r squared sine squared theta r dr d theta. Okay, so let's see, what does that do? Alright, so I have 0 to pi, 1 to 2, distribute the r gives me 3r squared cosine theta plus 4r cubed sine squared theta dr d theta, and I'm basically back to what I've known as rectangular coordinates in the past here, right? So let's work the dr's first. So still 0 to pi, right? This is going to go cubed, so that's just going to be r cubed cosine theta. This one is going to go r to the 4th sine squared theta, and we're going to go from 1 to 2 d theta, right? So 0 to pi, let's see, that's going to be, what do we have here? 2 cubed is 8 cosine theta. 2 to the 4th is 16 sine squared theta. Minus, let's say it's going to be cosine theta plus sine squared theta d theta is now going to give me the integral from 0 to pi of 7 cosine theta plus 15 sine squared theta d theta. So now I'm down to an ordinary integral. This one's a little bit tricky to solve. We're going to need a trig identity here. So let's recall that trig identity. Okay, the trig identity here that we're going to use is that the cosine of 2 alpha is equal to 1 minus the sine, 1 minus 2 sine squared alpha. This implies that 2 times the sine squared of alpha is equal to 1 minus the cosine of 2 alpha, which is ultimately going to imply that the sine squared of alpha is going to be 1/2 of this, 1 minus cosine 2 alpha. Okay, so how do I apply that here, right? So that means, remember that we have the integral from 0 to pi. This one is 7 cosine theta. That's not an issue. But now I'm going to take, let's see, it's going to be 15 over 2 times 1 minus cosine 2 theta. Gets me out of my issue there, right? Because this is now going to be the integral from 0 to pi of 7 cosine theta plus 15 over 2 minus 15 over 2 cosine 2 theta, right? So that becomes 7 cosine theta plus 15 over 2 minus, or theta, right? Oh, we're integrating. Sorry, I missed the sign. Yeah, 7 is now going to be sine theta, right? We've taken the integral. Plus 15 over 2 theta minus now 15 over 4 sine 2 theta from 0 to 2 pi. The nice thing is all the signs go to 0. So this is going to be 0 plus 30, or 0 to pi. It's not 2 pi. 0 to pi, so that's not 30. That is 15 over 2 minus 0 minus 0 plus 0 minus 0. So that means that this thing just works at 15 pi. There we go. 15 pi over 2. All right, so a little bit of crazy work there with the trig identity, but we can get from polar to an answer probably quicker than we could trying to do that in a rectangular fashion. So there you go, double polar integrals.